as types in the simply typed lambda calculus in terms of those types. So it's category of types in the lambda calculus, simply typed lambda calculus. And now I claim that this is a Cartesian closed category. So let's just check that that really is the case. Well, I think it's almost immediate, right, that these are going to give projection operations coming from this is going to be the product, this is going to be the projection operation, right? This is going to be the pairing associated with the product. This is going to be the transpose of a function that we needed before. And then the evaluation, I think you can figure out for yourself, comes from this, right? If I take the object that's the product of these two things, take the two projections, and then I apply one to the other, that's going to be the evaluation. Yeah. So I think I won't go through the details except to note that to make this a Cartesian closed category, it turns out that we need to identify certain proofs. We don't need to do it to make it a category. It just is a category. We checked that last time. But to make it really be a Cartesian closed category, we need to identify some proofs. And in fact, it's easy to say which proofs need to be identified. It might have been that the congruence relation or the equivalence relation on proofs was something that's really hard to specify, right, in order to make it Cartesian closed. But it turns out it's very simple to specify. It has some familiar axioms. Namely, if we take two proofs, alpha and beta, and we pair them up, and then we take the first projection of that, we need to identify that with the proof alpha. If we think about what's happening, right, in natural deduction, we're saying, well, take a proof of A and a proof of B. Let's switch to uppercase here just for fun, right? And then take the pair alpha, beta. That's a proof of A and B. And now take the first projection. Well, now we've got a kind of a detour here, which started out from a proof of A, and it ends up with a proof of A. And now what I have to do is identify a proof that goes straight to A and a proof that goes all the way to A through such a detour. Yep. Yep.
Is it possible to weaken the definition of CCC?
Yeah, sure.
To not have to do this on
Yeah, it has a certain structure, but those things are not universal. Right? It has a kind of a weak CCC structure. So similarly, we have to do it with a second projection, and then we have to add the rules of lambda conversion, right? We have to say that if I take lambda x of some beta, and then I apply that to some alpha, say that that's beta with alpha for x, and similarly, if I take lambda x of f applied to x, that that's f as long as there's no free x in f. Well, these are just the usual rules of beta-eta conversion, right? So that's what's sometimes called beta-eta equivalence. So if you add the rules for beta-eta equivalence plus the congruence laws that say substitute equals for equals everywhere, and you look at the congruence that's generated then on the set of all the lambda terms, it gives you a new category, and now that category is actually Cartesian closed. So it's easy to kind of check it. It's routine. It's in the notes. But you should think through it yourself or read it for yourself. And it shows you that this category of types in the lambda calculus really is a Cartesian closed category. Now, I'm out of time, but I would like to mention one consequence of this fact, which I think is worth noting. We've actually done the proof. It's just a question of formulating the fact that we have just established in a different way in terms of deductive completeness of the calculus of beta-eta equivalence. So we could say, let's define a theory in the lambda calculus, theory T in the lambda calculus to be the following. We have some basic types. And some basic terms, which we throw in. They don't have to be of basic type. They can be of any old type. So let's say A of type X. And some equations between terms of the same type. And we can have a whole set of types, a set of terms, and a set of equations. And then we generate, using the beta-eta reduction, that is, using these equations plus those equations and substituting equals for equals, we can define this notion then of T proves, for some terms here, let's say S and T, well, some other terms, A equals B of some type X. So that's a relation that we're interested in. It's the algebraic theory determined by those basic types, terms, and equations, right? So for example, you could formulate the theory of groups in this way as a lambda theory. You could formulate any algebraic theory in this way as a lambda theory. But you can also formulate some higher order theories in this way because we have function types as well. And so we can have terms of function type. A nice example is Dana Scott's theory of a reflexive domain. This is a domain D such that when you make D to the D, you can have a embedding retraction pair or even an isomorphism between these two things. So put in a section and put in a retraction and then put in an equation that says that R after S is the identity on D to the D. You could do the other one too. S after R is the identity on D. So there's an example of a theory in the lambda calculus. It has one basic type, two basic terms, and two equations. So there are lots of such examples of a theory in the lambda calculus. And then define a model. Define a model of such a theory T in a Cartesian closed category C. Well, that's an assignment of basic types to objects in C, and basic terms, say A, should then be, if it's a closed term, it should be a map like this, or the corresponding thing in C. So in C, such that, and now what I have to do is extend using the Cartesian, so this is the assignment of the basic data, yeah? And now I extend to all terms. So now extend, given this basic data, extend the interpretation for any term, T1 into, say, some type A for any T of type A, and in particular for any term F of type A arrows B, then I get an interpretation F as an arrow in my Cartesian closed category. And so now the definition of a model is I assign the basic data like this in the Cartesian closed category, I extend it to all terms like this, and then when I interpret my things occurring in the basic equations, S and T, S actually comes out to be equal to T in the as terms of type X. So if you specialize this to familiar cases like the theory of groups, and you interpret it in the Cartesian closed category of sets, a model will just be a group. Okay? So it captures the usual notion of a model of an algebraic theory. If I do this for that theory, a model of that theory will be what's called a reflexive object in the Cartesian closed category. It'll be an object D such that the exponential of D with itself will admit a retract from D. Yeah? A section retraction pair from D. So it captures exactly kind of the intuitive notion of an interpretation of the lambda calculus into a Cartesian closed category. And now the theorem is the completeness theorem. the theorem says so this is something like Cartesian closed category completeness for lambda calculus. For any theory T in the lambda calculus, one, the following are equivalent, or let me put it this way. For any terms, closed terms, say, closed terms, we can always close them up by changing the type. For any closed terms, A and B of any type X, if T proves A equals B from the axioms for the theory, the basic equations for the theory, then, and only then, is it the case that the interpretation of A equals the interpretation of B in any model, or every model, T model, of course, in any Cartesian closed category. So if T proves it, then it's true in every model, and moreover, if it's true in every model, T must prove it. So it's just like the completeness theorem for first-order logic with respect to set-valued semantics that we've already talked about, but now we're talking about provability in the lambda calculus, and the semantics are in Cartesian closed categories. And then another notion of provability in the lambda calculus is the existence of a closed term of a type. That corresponds to the lambda calculus as the proof theory of propositional logic, because the existence of a closed term of a type means there's a proof of the corresponding proposition in, say, a natural deduction calculus for the propositional calculus. So there exists a closed term, say T, for some type X, just in case in every T model in a CCC, the type interpreting X has a map from the terminal object. So there exists a map from the terminal object. So it's a very strong sense of completeness. It's completeness in this deductive sense, and it's completeness of beta-eta equivalence with respect to CCC models. So what this tells us really is that you can, the lambda calculus, in a certain sense, the lambda calculus, at least with the simply typed with products and function types, is really equivalent in a sense that, if I had more time, I could make precise as an equivalence of categories to the notion of Cartesian closed category. There's a way to turn any lambda calculus into a Cartesian closed category, and there's actually a way of going back, and we could define morphisms here and get an equivalence of categories. It's a very tight, precise correspondence, which can in fact be cashed out like this in terms of a completeness theorem. And it's quite nice to look at the, if I can just say one more thing, this was the proof theory of propositional logic. We can do a similar thing here with the propositional logic itself, intuitionistic propositional calculus, say with conjunction, implication, even with disjunction, is going to be in exactly the same way equivalent to the notion of a poset CCC. Well, let's do it without the disjunction first. A poset CCC is just a Cartesian closed poset, right? It's like this first example that we had of the intuitionistic propositional calculus as a poset, but we can also add the other operations here, for example, the disjunction, and then we get the notion of a Heiting algebra, respectively, Boolean algebra. Let me spell it out. So I don't have time to do that, but exactly the same correspondence holds here, where this is the kind of poset collapsed case of this, which is the proof theory of the thing. Okay, so that's enough for now. Next time I will talk about naturality, natural transformations, and there's a special case of this completeness theorem that's of some interest, and that is looking for specific Cartesian closed categories which suffice to test for completeness. These are general abstract Cartesian closed categories. It's very interesting to know that this completeness theorem holds as well when you specialize to Cartesian closed categories of a very special form, namely functor categories, or even functor categories where the exponential category, the exponent, is a poset, P, and these are, I think, reasonably called Kripke models. So there's a Kripke completeness theorem for the simply typed lambda calculus, which follows from this result by a kind of specialization result about special Cartesian closed categories of this form. Okay, thanks a lot.